Hello and welcome to our channel again. So here I am Suraj with a new video of mine on the second part of the quantum harmonic oscillator. So in the first part we have discussed about the quantum harmonic oscillator and also the classical harmonic oscillator, and we have derived our equations. And in this video we are going to describe a fully quantum harmonic oscillator wave functions that will describe its different types of the quantities. So we have derived our equations like this in the form of the ladder operators. A the moving operator, this is the raising operator, and this is equals to the Hamiltonian operator divided by h cut omega plus 1 by half. So we have derived till this. Now we are going to execute our this particular derivations, and finally our final wave functions for our quantum harmonic oscillator. Okay, so let's start our video. So what we can do now is that we can just put 1 by half on this left hand side, and what we get is that a cap minus and a cap plus, and here minus 1 by 2. Okay, and here cross multiplication of h cut omega, here we can write it as h cut omega is equals to the Hamiltonian operator. So we have write our Hamiltonian operator in forms of our raising and the ladder operators. So as you can see that we have written our Hamiltonian in the form of the ladder operators. As you can see that this is the first form of our Hamiltonian from which we start our derivation, and now we come to another definition of the Hamiltonian in the form of the ladder operators. Now we are going to use the real applications of the ladder operators. So what I have told you about the ladder operators is that it's just increase or decrease the energy of your system. Okay, it just increase. That's why this particular is known as the lowering operator, because it's decrease your energy, and this is known as the raising operator as it's increase your energy. Okay, so can we write it like this is that we have told you that whenever you apply this particular lowering operator, it will just decrease your energy. So can we write, and we can be repeatedly applying this particular lowering operator to our wave function, of the harmonic oscillator, completely applying. So let's say it is sine naught, and completely applying the particular lowering operator, what we get is that it certainly becomes 0. Certainly our energy becomes 0. Can we write our this particular term here, that continuously applying our this particular raising operator to the lowering operator to the wave functions, the energy decreases to the 0. So yeah, we can write it. And what we found is that we have derived our Hamiltonian in the form of this raising and the lowering operators. It means the wave function that we have written will give out the harmonic oscillator wave functions. Okay, so let's substitute the values of a minus. Okay, so I have written here the value of the a cap minus as 1 over root under 2 m omega h cut, and iota p cap plus m omega x. So let's write out here. So after writing this, what we can get is that a cap, okay, 1 over root under 2 m omega and h cut here, and in bracket can I write it as iota p cap, where p is the operator of the momentum, and m omega x is equal, and here psi naught, and here psi naught is equals to the 0. Okay, so we have write over this particular expression. So we can also simplify this equation in a manner that if we just take this particular side to the right hand side, it will become 0, and our expression can be written as iota p cap plus m omega x, and here bracket psi naught is equals to the 0. Now if you remember, in one of my lectures I have told you about that the momentum operator formula is equals to the negative of the iota h cut d by dx. Generally here is partial derivative. But here we are not going to deal with more than one variables. That's why we put here not the partial derivative, just the ordinary derivative. So now we can substitute this value like this as iota into iota negative h cut d by dx and plus m omega x, and here can be written as sine naught is equals to the 0. So if you have remember, then iota into iota is equals to the negative 1, and negative negative become positive, and our expression can be written as the h cut d by dx and plus here m omega x, and here we can write it as in the form of the sine naught equals to the 0. Now we can easily solve this particular differential equations. So the differential equation that is here is very easy to solve. So I'm going to solve here the differential equation here. First of all, I have to write in more simplified form. So how I can write this in more simplified form? So you can write is that multiplying this, you can get as h cut d psi divided by dx, and here is sine naught, and plus you can see that it will equal to the m omega x psi naught is equals to the 0. Okay, so in a more suggestive form, how I can write this is in a more suggestive form, we can write as d psi naught divided by the dx is equals to the negative of the m omega x, and divided by here h cut and sine naught. Okay, so this is our thing, and after doing some of our separable solution, we can solve this particular differential equations by the separable solutions method. It means to put your psi naught variable in the psi naught and x variable to the x. So can we write it as d psi naught divided by psi naught is equals to the negative of m omega x divided by h cut dx. So this is a differential equation. So what is the solution of this particular differential equation? So I'm going to solve here our differential equation. So the thing is that just do the integration on the both side, which will result at d sine naught divided by our sine naught is equals to the negative of the m omega h cut, sorry, m omega divided by h cut, m omega divided by here h cut, and integration of x dx. So what is the integration of 1 over x? So just like here 1 over x as integration log of x ln x, this integration is equals to the ln sine naught is equals to the negative of the m omega divided by h cut and here x squared. So we have to write our this expression. So how we can write it? So can we simplify this as sine naught is equals to the e to the power minus m omega divided by the h cut x squared. So how I do this? So how I do this is that just put both side log. What you will see, if I put here both side log, then natural log of psi naught is equals to the log, and log e will cut out, and we left with this particular expression. It means we just put our this particular expression in a more familiar way as psi naught is equals to the e to the power negative m omega h cut x square. But remember, here is a constant normalization constant a in the quantum mechanics. So I'm directly going here to write out our solution that we have obtained, and our solution is equals to the sine naught. Sine naught is equals to the a and e to the power negative m omega divided by the h cut x square. So what is A? A is the normalization constant. If I have seen my video, I've explained that how to find out the A. So I'm directly going to write out the value of A. Maybe in some later videos I will describe that what exactly the value of A is. So the value of A is root under m omega divided by pi h cut, divided by the pi h cut. How this came? So you can generally write out the formulas, and you can also find out that why the value of normalization constant, which is A, is this. So it is a pretty easy to evaluate, and I think that you can also solve this particular thing. Now m omega upon h cut x square. So this is our wave function. But remember, the wave function that we have obtained is the, you can say that, ground state wave function. Ground state wave function. But we have to evaluate wave functions which we apply our raising operator. It means, remember, the particular wave function psi naught that we obtained is the ground level. You can say it is a ground level wave functions, and you have to find out for any particular n terms we can find. For n is equals to the 1 2 3 4, you have to find out your particular wave function. So this is the particular wave function that do not describe for any n terms of our wave function. This is our ground wave function. So how we can write our n wave function? So the n wave function can be written as psi n x, can be written as, remember, this is the ground state wave function of harmonic oscillator. But someone asks you to find out for not ground state, for something like 1, for something 2 3 4 5 6. What you will do, you cannot find for any of the n values through this particular wave function that we obtained, which is psi naught. So there is a general formula through which you can obtain it. So formula is that psi naught x, and here a1 a, and let's an a cap plus, and here psi naught. Okay, I knew that you will ask me that how I write this. What is this? So the thing is that this describes only the ground wave function. This describes only the ground wave function, GWF. I will write it as ground wave function, not for any arbitrary wave function. If you will, anyone asks you to find out for psi is equals to the 1, 2, 3, 4, 5, 6, 7, you cannot find it. But you can find it by this psi and x. Psi and x. And here a n is the normalization constant. A n is the normalization constant, but remember, a n is not same as root under m omega upon pi h cut. It is different. It depends upon your value psi 1, 2, 3, 4. It is not same as a here, which is m omega upon pi h cut. Okay, and what is this? So this is the raising operator. But why? I have told you that whenever you apply the raising operator to the wave function, it will just increase your energy. So the thing is that this particular psi naught is your ground wave function, but if you continuously applying your this particular raising operator, you will get for any particular psi 1, psi 2, psi 3, or whatever this is. That's why I have written here a cap plus, which is the raising operator. This is increases your energy. It means your wave functions. So this is the general formula for finding the wave functions for any arbitrary n, but this is for only ground state. And finally multiplying it by the psi naught. Finally multiplying it by the psi naught. Okay, so let me show you something. So someone asks you to find out for psi n is equals to the 1, let's say. N is equals to the 1 if someone asks you. How you can find it? Putting the value of 1, you will find out that this particular quantity is going to be 1. A and your particular quantity is going to be 1. So maybe in the next video I will try to evaluate your particular doubt regarding that, why I have written here psi n x is equals to the a n, and here the raising operator is there. Here you can see that I have applying the raising operator and psi naught. So I will give you some examples in the next video through which you can understand it. But for now, you understand that the wave function that I've written is for the ground state. But this psi n x can be used for wave function for 1, 2, 3, for any wave function. Remember, for any wave function. examples in the next video, because in quantum mechanics example is very important. So by examples you can generally go into very deep inside that you can't go only by reading the theory. Okay, so this is our particular expression which can be used to do our wave functions in harmonic oscillator for any n, for any arbitrary n, maybe 1 2 3 4 5 6, for any n, but this is only for ground state. Okay, we have derived our wave function, but how we can find out the energy of your harmonic oscillator? How we can find out the energy? So the thing is that the formula that I have written here, which is the Hamiltonian formula, which is regarding to the, okay, I will write it here. Okay, so the thing is that how you can find out the energy? We have find out the wave function, but where is the energy for this? So if you have carefully looked at one of my lectures, I have written that a plus and a minus minus 1 by half, and here h cut omega is equals to the Hamiltonian. Yes or not? Yes. And what is Hamiltonian? Hamiltonian is the total energy. Hamiltonian is a total energy. So we can write it as E is equals to the E is equals to the A cap minus A cap plus minus 1 by half h cut omega. So generally here should be not minus, here should be plus, plus minus. Here should be not minus, it can be plus. Okay, it can be plus. Now what we can do is that, yes, so here I have forgot writing our sign, not sign here. So this is my fault that I have not write this sign, not sign, sorry. Okay, now we can evaluate it. So our energy psi naught can be written as, okay, if we multiply our psi naught to this, so we are going to find out an energy for our ground state wave function. For ground state we are going to find out our energy in the harmonic oscillator. And what we see that in ground state, when you are applying continuously applying our lowering operator, a naught psi is equals to the 0. It means if I multiply psi naught to this particular quantity, it will become 0, and what we are only left is with the 1 by half h cut omega psi naught, because we multiply psi naught to this, then a and this particular and this particular will multiply to become 0, and then all the equations become 0 here. Why? What we only left with is 1 by half h cut omega, and our correspondingly energy is equals to the 1 by half h cut omega. But remember, we derived our energy for our ground state. So but what about for n is equals to the different values? For n is equals to different values, we are going to find out the energy. How we can find it? Because this is the energy only for a, you can say that ground state, but where is the energy for the another states? So you can just add here an x and another term, which is written as E is equals to the, see here, n plus 1 by half h cut omega, where n refers to your energy and refers to any state. For example, for n is equals to 1, for n is equals to 2, you can find out. But here I am going to tell you another remark, if a property, that if you put down the value of n is equals to the 0, you will get also the value of the energy. And this is the thing in the quantum mechanics, that in the quantum mechanics, even if you put the value of n is equals to 0, there is a still energy, and this is called the 0 point energy in the quantum mechanics. It means there is no zero value defined in the quantum mechanics. A particle have a certain amount of energy, not a zero energy in the quantum mechanics. It have a certain amount of energy, and that's why I'm telling you that this is the quantum mechanics. This is the quantum mechanics, that even in the ground state, the particle has some energy, which is, if you put the value of n here, n is equals to the 0, you will generally get out the expression here, which is 1 by half h cut omega. It means even the energy is defined for a particle can't have zero energy in the harmonic oscillator. A particle can't have zero energy in the harmonic oscillator. So this is the remarkable thing in the quantum mechanics and the harmonic oscillator, and this is the expression for our energy. So this is our today's video where we expressed our wave functions in a more natural form for any value of n, and we also defined our energy. And what we see that in quantum mechanics, particle can't have zero energy in harmonic oscillator. A particle can't have zero energy. Zero energy is not defined here. So this is the property, and this is the remarkable property in the quantum mechanics, how beautiful the quantum mechanics is. So this is my today's video on the harmonic oscillator, and in the next video maybe we are going to discuss about some examples so you can understand it in a very good way. Because if you do not do the questions in the quantum mechanics, then it is highly likely that you don't actually understand it. That's why doing questions and examples is also very important. So maybe in our next videos we are going to dedicate our things in the question solving. So this is my today's video on the classical harmonic oscillator, and we have derived our some of the expressions here. So thank you for watching my video.